the last class we have seen a reference quantity, the m star. So, we will extend that to a new reference quantity, and we will come back to the area variations and the changes of properties due to area variation in this lecture. So, the first thing is that we will introduce a new reference quantity. So, we will just try to see the importance of T0 in relation to V. Okay. During this process of trying to understand the importance of T0, we will introduce a new quantity. So, we will go back to the TS diagram. So, I had state 1, I isentropically made the velocity to be 0 at the stagnation point. So, that is a 0 condition where my m is 0 or the velocity is 0. Okay. We have also seen how the m equals 1 condition produces a new reference quantity, which we call it as V star, which is equal to our velocity of sound A star at the same condition. And we look at the equations. Your Cp T0 is Cpt plus V2 square by 2. Okay. So, this is your total enthalpy. This is your kinetic energy and this is your static enthalpy. So, what does this equation tell you? So, if I have a gas of this much total enthalpy, that is balanced between the kinetic energy and the enthalpy of this, or to put it in the other way, I start with a gas of total enthalpy of Cp T0, okay, where the velocity is 0. Now, if I want to generate a velocity from this gas of with this total enthalpy, I have to compromise here. The balance is between the total static enthalpy and the kinetic energy. So, the energy that is lost from here to generate kinetic energy is in the enthalpy. So, some enthalpy is lost to get a kinetic energy. Now, that is how you get this relation, where we have seen this distance to be V square by 2 Cp. Now, if the whole of the energy is converted to kinetic energy, what happens? If the whole of the kinetic total enthalpy is converted to kinetic energy, obviously you get T0 equals V square by 2 Cp, where the whole of this enthalpy is converted to the kinetic energy, implying your static temperature is 0. Okay. Or this is your V max, that is the maximum possible velocity you can get from this. Okay. Or I should be writing this as the maximum you can get, but assuming Cp to be constant during the process, I can replace this as V max. Okay. So, that is the maximum velocity you can get for a given T0. So, if I have a gas at T0 equals some temperature, there is a limit to which I can get the velocity. So, the maximum velocity I can get here is T0 into 2 Cp, which is 350 into 2 into 1005, which is 11 meters per second. (350 into 2 root. So, this is the maximum velocity with which you can get if the stagnation temperature is this. So, you cannot achieve a velocity greater than this with this stagnation temperature, that is the meaning of this. So, the total enthalpy of this gas is this multiplied by Cp, and that is converted completely to kinetic energy, this is the velocity. And in the process your static temperature reduces to 0 Kelvin, which means in the Ts diagram here, that state is somewhere here where along the axis this is 0, my state is somewhere here on the axis. This is my Vmax, maximum velocity that can be achieved. So, this distance would be Vmax square by 2c. If that is the case, what would be the Mach number? This approaches to infinity. So, this is something which you cannot achieve in reality, that is a reference point as our stagnation point which we have done. So, we can use this quantity Vmax also as the energy associated with the gas. If m equals infinity, your sin mu is 1 by m is now the Mach angle is 0. So, as we have seen earlier, as the Mach number increases, the Mach cone, the cone angle keep decreasing. At m equals 0, m equals infinity, your mu is now small, very small. Okay. Now, if that is the case, what would be the P0? I want to draw this in your PV diagram too. What would be the P0? In the PV diagram, I have a P0. This is an isentropic process. So, I have an isentropic process here. So, this process 0, 1 and this condition, the max condition, all lie in this particular line. So, this is my constant entropy line. So, this point is my T0. Now, T0 keeps coming down. At Vmax, I have my T equals 0, but what about P? P also keep decreasing, but what will be the P at Vmax? Since the process is isentropic, you can write P0 by P to be T0 by T to the power gamma by gamma minus 1. Okay. So, for a given P0 and T0, if T approaches 0, your P also approaches 0. So, your pressure also approaches 0. So, you would get it along this line. Okay. So, if I have a large stagnation temperature, I can get a associated Vmax, which is my new reference quantity. Now, before coming to the quantity variations due to area change, which is what we have been doing in the last few classes, we will see how this essentially varies with Mach number, which we have derived to be of this form. Gamma by gamma minus 1. Okay. So, this is the relation that we have derived for the pressure change as the fluid undergoes some process between stagnation point and state 1 in this particular diagram. Now, this variation depends on Mach number. So, what I am going to do now is I will expand this using binomial theorem as the following: 1 plus n into x plus n into n minus 1 by 2 factorial into x square and so on. Okay. So, here my n is gamma by gamma minus 1 and my x is gamma minus 1 by 2 m square. So, my p 0 by p is 1 plus gamma by gamma minus 1 into x is gamma minus 1 by 2 into m square plus I will write one more term, which is gamma by gamma minus 1 into gamma by gamma minus 1 minus 1 into 1 by 2 into x square is gamma minus 1 by 2 the whole square into m square plus. So, which is now 1 plus gamma by 2 m square plus gamma by 2 into 1 by 4 into m power 4 plus. So, this is nothing but 1 plus gamma by 2 m square plus gamma by 8 m to the power 4 and goes on. So, what does this equation tell you? Let us take PV diagram or 1 by rho diagram. From state 1 to 2, if I have an isentropic process from 1 to 2, or because I have written here P0 by P, I will assume 1 as my stagnation condition and 2 as my static condition of state 1. So, I have a process between 1 and 0 or 0 to 1. So, I have a process from 0 to 1, which is not your condition where we have V max, V some point, some state in the flow. Now, during this process, my P0 by P goes in this particular fashion, which is a function of gamma and m. If I take only the first two terms, let us take only the first two terms. I am truncating my series after the second term. Okay. Now, if this is the case, this equation can be reduced to the Bernoulli's equation. I can write this as 1 plus, or I will start from Bernoulli's equation and reduce to this particular form. I write P0 equals P plus V square by 2 rho. P plus rho, I take P outside, so this would be 1 plus rho by P V square by 2. I multiply this both numerator and denominator by gamma. So, this would be P into 1 plus gamma P by V square by P gamma by rho into gamma, which is nothing but 1 plus m square into gamma by 2. Which is precisely what we have here. So, your Bernoulli's equation is a truncated equation of the full compressible flow equation. So, if your Mach number is very small, I can assume P by P0 is only the first two terms. So, if the Mach number is small, my P by P0 approximates to 1 plus gamma by 2 m square. How small is something which we will see now in terms of density. So, I can rewrite this in terms of density, where this is 1 plus gamma minus 1 by 2 m square to the power 1 by gamma minus 1. Okay. I do the same expansion here. So, rho 0 by rho is 1 plus n is gamma minus 1 into gamma minus 1 by 2 m square plus this. Again, if I take only the first two terms, this is 1 plus 1 by 2 m square. Okay. Now, if my m is, let us say 0.3, if m is 0.3, then rho by rho 0 is 1 plus 0.3 square by 2. This is around 1.045. It is approximately 5%. Okay. So, your fractional change in density due to your speed of the fluid or the velocity of the fluid is just 5%. Is approximately 5% if it is 0.3. Okay. So, if I use that 0.3 here, then my fractional change in pressure when I do this process, okay, that is equivalent to what you get from the Bernoulli's equation instead of using this. That is the point. So, if I decide I cannot accommodate 5%, I can only account only 1%, or I can extend it to say 20%, then this would be quite large. So, instead of 5% here, this would be 1.3 or If you can live with it, you can live with it, but generally what we do is we take this as a demarcation where we say the flow is incompressible if the Mach number is less than 0.3, and if it is more than 0.3 we assume that to be a fully compressible flow, meaning at 0.3 we can truncate our series after the first two terms. Otherwise we have to take the full series, which is essentially this equation. So that is what you see when the gas is expanded or to a point from a given energy content. So the given energy content is now decided by T0 and P0, and with that energy content you are getting a velocity which is less than Vmax, as we have seen. So that Vmax, to get that Vmax, some energy is being taken from the total energy content, and in the process the pressure change that you see here, if it is less, Mach number is less than 0.3, it is incompressible, greater than 0.3 it is compressible, where we need to use the full set of equation. Okay. Now that is how the properties change during the expansion process, or the total energy of the gas is now producing some kinetic energy. Now what we need to do now is, in the area relation that we have been working on the previous classes, how does this fit in there? How does the property change P0 or dP by P or some fractional change that is happening should be, how does it change according to the Mach number or the velocity? Okay. So let us start from the equations where we have left in the previous class. So we had written dH equals V TdS equals dH minus V dP. We assume to be the process to be an isentropic one. So this is 0. So my dH is dP by rho. Now from the pressure energy relation we have dP by rho to be or from the enthalpy relation dH plus dV square by 2 plus dQ plus dWs equals 0. If we assume no heat, no shaft work, we will end up with dH equals minus V dV, which we substitute here to get dP by rho to be equal to minus V dV. Now we will start from that equation. I want to find dP by P, for which I have taken rho to the other side, V dV divided by P. I also multiply and divide by V. I also multiply and divide by gamma. So this would be P gamma rho is my velocity of sound. So that would be V square by A square into dV by V into gamma. This is nothing but gamma m square dV by V. So for the process, some process that is happening, the pressure change due to your velocity change is what is written here. Okay. We will come back to this. Now let us look at the temperature change. So your dH equals minus dV square by 2. So this is Cp dt equals minus V dV. So, I divide dt by t, I take Cp here, I replace Cp as gamma r. So, I have divided by t, so there is a t here, gamma r by gamma minus 1 into t into dV I multiply and divide by V. So, I have taken Cp to the other side, which is now written as gamma r by gamma minus 1 divided both sides by t. So, there is a t here, then multiply and divide by V. So, that would be V square. So, this is minus m square gamma minus 1 dV by V. So, this is the change in fractional change in temperature due to the velocity change. Okay. Likewise, what we have derived in the other lecture was d rho by rho is minus m square dV by V, right. Okay. So, this is your fractional change in density due to fractional change in velocity, which typically goes as minus m square. So, if there is a change in a positive change in velocity, there is a negative change in density. So, for to have a velocity increase, you need to decrease your density, which is what you had seen in the previous PV diagram, where if this is my isentropic process, this is PV. Okay. For an isentropic process, from stagnation state to some static state where you have generated a velocity, the volume has increased, which means the density has gone down. So, this is an expansion process. This is an isentropic expansion where you are getting your velocity from your total enthalpy, which we had seen to be Zp T0. Okay. So, that enthalpy is going to produce a fractional change in velocity. In the process, you are going to have decrease your density, whereas here temperature also decreases, your pressure also decreases, because there is a minus sign associated with this. Okay. Now, we include this along with our area change. Okay. So, this process has nothing to do with your area change, but now given the total energy and how we know how to produce a velocity, and now we know how the pressure, temperature and density changes due to the fractional change in velocity, we relate that to now area change. Okay. So, we will like in the previous class, we will gather this equation and write it down here and try to see what it means. So, let me write the first equation, dP by P equals minus gamma m square dV by V, dt by T is minus m square gamma minus 1 dV by V, and your density change d rho by rho equals minus m square dV by V. Now, what is dV by V in terms of area? From previous lecture, dV by V is minus 1 by 1 minus m square into dA by A. Now, if I substitute this quantity here, So, let us say substitute equation 4, this is equation 3, this is equation 2, this is equation 1. So, I am going to substitute equation 4 in 3, 2 and 1. So, my first equation dP by P is now minus gamma, minus and minus would cancel out. So, this would be gamma by gamma into m square by 1 minus m square into dA by A. Okay. Now, dt by t is minus and minus cancel out. So, this would be gamma minus 1 into m square by 1 minus m square into dA by A. Now, let us look at the density. Minus and minus cancel out. So, I would get m square by 1 minus m square into dA by A. Okay. I will write this along with it so that we can compare. Now, if you look at this first the left hand column equation, these are all m square. Okay. So, whatever relation we have been talking about V and fractional change in velocity with fractional change in pressure or temperature or density holds for any Mach number, because now this is a positive quantity. Okay. So, if there is a positive change in velocity, there is a negative change in density, there is a positive change in velocity, there is a negative change in temperature or pressure. But whereas when it comes to area, we have a problem because it is 1 minus m square. So, the relation is going to change depending on the Mach number. Okay. So, let us write first if m greater than 1. So, we have already seen how your d rho by dV change with d rho by dA change with Mach number. So, if I draw dV by V divided by dA by A, then I am going to have a discontinuity somewhere here at m equals 1. So, these solutions what we have written here is not valid at m equals 1 because there is a discontinuity, and we are not accounting discontinuity. Why? Because we have assumed isentropic flow. Okay.